Assalamualaikum and hi to our lecturer, Professor Madia Dr. Zamali, and I would like to start our presentation about our project in this subject, Ordinary Differential Equation, ODE. We choose application of Newton's law of cooling and warming. Now, I would like to introduce our group members with me, Rana Maisarah binti Rosdi, Emilia Nur Adrin binti Muhammad Azam, Nurul Farhanis binti Zuraidi, and Zufira Alia Khairunisa binti Zaidi. Now, I want to continue with the introduction of ODE. What is ODE? Ordinary Differential Equation, ODE, is an equation that involves the derivative of one or more dependent variables with respect to a single independent variable. Second, ODE will provide a mathematical framework to the model of real-world phenomena depending on a variable changes. That is essential for engineering and science too. So next, we move to introduction of cooling and warming. Newton's law of cooling and warming is a process to describe the temperature of an object changes over time when it is placed at a different surrounding temperature. The model is formulation as d capital T over d small t equals to k open bracket T minus Tm. Capital T in the bracket of small t0 is equals to capital T0. D capital T over d small t is the rate of change of the temperature. K is constant of proportionality. Tm is the temperature of surrounding object. Tt, temperature of the object at time t. T minus Tm is the difference between the object's temperature and its surrounding temperature. Capital T0 is the initial temperature. And lastly, small t0 is the initial time, usually 0. The temperature of many objects can be modeled using a linear first order differential equation, like in this case, when an ice cream is left outside from the freezer, it will gradually melting. The graph between the temperature over time of an ice cream is known as cooling curve. The rate of temperature is determined by the slope of tangent to the curve at any point.
The problem statement is, on sunny afternoon, Ayah decided to bring ice cream from her house to enjoy with a friend at the beach. The ice cream was taken out from the home's freezer and placed in her car. The distance between the house and the beach was quite far, and during the journey, the ice cream was exposed to the surrounding air with a constant temperature of 30 degrees Celsius. Initially, the temperature of the ice cream was negative 18 degrees Celsius. After 1 hour of travelling, when Ayah arrived at the beach, the temperature of the ice cream has risen to negative 6 degrees Celsius. The question is, determine the time needed for the temperature of the ice cream to reach negative 12 degrees Celsius. And question 2, the temperature of the ice cream after 1 hour and 50 minutes. The first question is, determine the time needed for the temperature of the ice cream to reach negative 12 degrees Celsius. Given from the question, temperature of the surrounding is 30 degrees Celsius. Initial temperature is negative 18 degrees Celsius, and let Tt be the temperature of the ice cream at any time, which is in this question, Tt equal to negative 12 degrees Celsius. Temperature after 1 hour is negative 6 degrees Celsius. The differential equation related to this problem is dt over dt equal to k multiplied by t minus ts, equivalent to dt over dt equal to k multiplied by t minus 30. And we solve the equation by separating the variable and integrating both sides of the equation. Integral dt over t minus 30 equal to integral k dt. And we get ln t minus 30 equal to kt plus c. Calculate it, and we get t minus 30 equal to exponential to the power of kt plus c. And we get tt equal to a exponential to the power of kt plus 30, when c equal to exponential to the power of c. The general solution, we get tt equal c exponential to the power of kt plus 30. Second step is apply the condition given to find the value of c and k. To find the value of c, the question given temperature at 0 time is negative 18 degrees Celsius, equal to 30 plus c multiplied by exponential to the power of k at 0 time. Calculate it, and we get c equal to negative 18 minus 30. C we get negative 48. And t equals to 30 minus 48 multiplied by exponential to the power of kt. Next, to find the value of k, the question given temperature after 1 hour is negative 6, equal to 30 minus 48 multiplied by exponential to the power of k at 1 time. And we get exponential to the power of k equal to negative 6 minus 30 divided by negative 48. And k we get ln 3 over 4. And we get t equal to 30 minus 48 multiplied by exponential to the power of ln 3 over 4t. Third step, we already know that tt equal to negative 12 degrees Celsius. So in this question, 30 minus 48 multiplied by exponential to the power of ln 3 over 4t equal to negative 12. We calculate it and we get exponential to the power of ln 3 over 4t equal to 42 divided by 48. And we get ln 3 over 4t equal to ln 42 divided 48. We get negative 0.2877t equal to negative 0.1335. To find t, we divide negative 0.1335 with negative 0.2877. And t we get 0.4641 hour. We change it to minutes and we get t equal to 27.8 minutes. So the final answer is it takes 28.7 minutes for the ice cream to be negative 12 degrees Celsius.
For part B, we are required to find the temperature of the ice cream after 1 hour and 50 minutes. First, we convert the given time into hours. 1 hour and 50 minutes is equal to 75 minutes. Dividing by 60 minutes give 5 over 4 hours. Next, we use the temperature function obtained earlier from Newton's law of cooling, which is Tt is equal to 30 minus 48e to the power of ln 3 over 4t. Then, we substitute t is equal to 5 over 4 into the equation. After substituting the value of time, we evaluate the exponential term. The value of e to the power of ln 3 over 4 multiplied by 5 over 4 is approximately equal to 0.6980. Then, we multiply this value by 48, which gives 33.504. Finally, we subtract this value from 30 and obtain t is equal to negative 3.504 degrees Celsius, which is approximately equal to negative 3.5 degrees Celsius. Therefore, after 1 hour and 50 minutes out of the freezer, the temperature of the ice cream is approximately negative 3.5 degrees Celsius.
Next, we proceed with problem statement 2. After enjoying a day at the beach, Ayah and friends decided to stop at a cafe near the beach. They bought a cup of freshly prepared tea. At the moment it was served, the temperature of the tea was 100 degrees Celsius. Since the tea was too hot to drink, they left it on the table to cool. The air temperature around them remained constant at 20 degrees Celsius. After 5 minutes, the temperature of the tea was recorded as 75 degrees Celsius. The question is, assuming the cooling process follows Newton's law of cooling, determine the temperature of the tea after 15 minutes. To answer the question, determine the temperature of the tea after 15 minutes. We use the formula dt temperature over dt time equals to k in bracket t minus tm. Given that the initial condition T0 equals to 100 degrees Celsius and T5 equals to 75 degrees Celsius. Given that the surrounding temperature Tm equals to 20 degrees Celsius, then we substitute the surrounding temperature into the formula, which is dt over dt equals to k in bracket t minus 20. And then we separate the variable. dt equals to t minus 20 equals to k dt. After we separate the variable, we integrate both sides, which is integrate 1 over t minus 20 dt equals to integral k dt. And we get ln t minus 20 equals to kt plus c. And then we eliminate ln, we multiply with exponential. So we get t minus 20 equals to exponential the power of kt plus c. And then we apply the initial condition. T0 equals to 100 degrees Celsius. 100 equals to exponential k in bracket 0 plus 20. And then we get the value of c, which is c equals to 80. And then we get dt equals to 80 exponential the power of kt plus 20. Then to get k value, at t equals to 5 minutes, 75 equals to 80 exponential the power of k in bracket 5 plus 20. And then we get 80 exponential k in bracket 5 equals to 55. And then exponential 5, the power of 5k equals to 11 over 16. And then we get 5k equals to negative 0.3747. To get the k value, we divide by 5. And k equals to negative 0.0749. And then we get tt equals to 80 exponential the power of negative 0.0749 plus 20. And then to answer the question, when t equals to 0.0749 in bracket 15 plus 20. And then we get the t value, which is 46.01 degrees Celsius.
Conclusion for this project is, at the end of this assessment, we can conclude that the application of first-order ordinary differential equation, specifically Newton's law of cooling, help us solve real-life problem involving temperature change. Through the example of melting ice cream and cooling tea, we demonstrated how mathematical model can be used to predict temperature over time accurately. This study shows that many daily life problems can be understood and solved more easily by applying first-order differential equations. Therefore, the application of first-order ordinary differential equations is not only important in mathematics, but also very useful in practical situations encountered in everyday life.